Hello! A year or so ago I brought you the floating Amiga Boing ball and it looks great. And as you can see, from above it is indeed a Boing ball. From the sides you can also tell that it's floating. Cool, eh? But there was something I wasn't quite happy with, something that just made it feel a little less authentic. And no, it wasn't because it wasn't bouncing. No, there was something else wrong. So in this video we're going to redesign the floating Boing ball and show you the new Amiga Boing ball 40th anniversary edition. So what's the problem with the floating Boing ball? Well, let's take a look at the original Boing ball demo. And if we ignore the sound and the bouncing, you'll notice something else. If you compare the two, mine spins on a perfect vertical axis, and the original, the ball is more on a diagonal axis. And this annoyed me, and so I created these, the Amiga Boing ball 40th anniversary editions. And there's quite a few things you'll notice that are different. First, unlike the original, this isn't a sphere. It's actually more blocky, just like the original demo. Also, like my original, they float too, as I'm demonstrating with a piece of paper. However, you'll also notice they're floating at an angle as well, but they still seem to be spinning vertically. Well, look what happens when I switch it on. Now that's much better. What do you think of that? You wouldn't believe how many prototypes went into this one, and I have to say I am very pleased with this new version. So, how does this magical wizardry work spinning on the wrong axis? Well, let's take a look at how it works, and how you can build your own. But before I do that, I just want to give a quick shout out and say thank you to all of my Patreon supporters. And if you want to support me in making future videos, then follow the links in the video description. So, how does it work? Well, like most of my crazy inventions, everything started in Tinkercad. So, let's have a look at the component parts. First, I have the actual ball itself, split into two hemispheres just like before. However, this time I didn't want the hassle of gluing them together. So if you look at the bottom of this one, you'll see these little teeth sticking out, and the other half has some strange indents. Well, there's also this spherical ring here as well, which you can print and it gets glued into the second piece. It's done like this to reduce how much support material is needed. Once completed, the two pieces will fit and twist together, meaning no glue is required, and more importantly, we can access anything inside if something goes wrong. But how does it rotate? Well, if you look at the top and the bottom half, you'll notice this little hole here. These are designed so you can insert a special aluminium rod at the correct length into these, which provides the access for it to spin on. But that alone wouldn't keep it at an angle. That's because we need to use this special piece. This has the magnet fitted onto the bottom. And by using the coil and power supply for the lights, we've also connected a motor here as well, which connects to one half of the ball, the other half just fitting into the other hole at the back. And when assembled together, it should look like this. The yellow bit you can see poking out is the top of the motor. The black disc here represents the magnet, and the orange bit here at the bottom is a spacer, more on that later. I've even designed a little shaft coupler to connect the motor to these rods, and they will be 5mm in diameter, and aluminium to keep them as light as possible as well as not being magnetic. And with that piece designed, the entire thing should look like this. Well, that's the theory anyway. It's possible I may need to make small modifications. That space at the bottom here is small enough to get the maximum amount of flotation, but large enough so everything should move smoothly. Sounds simple when I put it like that, but there's quite a bit more to it than that. When I built the original one, I printed the dome in white and then glued the red segments on to finish the effect. But now I have a printer that can print using multiple colours at once, which is very handy, meaning I can just print it all as one solid piece. It's going to be very slow, and I'm going to use a variable layer height as well to give the best quality. So let's get those parts printed. Unfortunately, the white PLA plastic I used to use, which was ever so slightly transparent, just doesn't seem to exist anymore, and I've tried so many different PLA plastics from so many different manufacturers, and they're all the same. So, I printed two versions to test with, one with opaque red and white, and the other one with transparent red and white. And you can see me showing them here. The opaque one looks stunning sitting on the desk, and I made a bit of a mistake with the supports, they're actually impossible to remove. If you didn't want to light this up from the inside, then this would be perfect, but when lit, the red actually looks a lot brighter than the white. It's such a shame. However, the other prints, with the transparent PLA, well, that just looks a little bit more like a Christmas decoration, and I kind of like the sparkle effect, so this is probably what I'm going to use. Next is to loosely assemble everything so you can see how it's supposed to fit together. You'll also need two aluminium, i.e. not magnetic, metal rods to connect everything up, and they need to be exactly the right size. To help with this, I've also printed a special guide piece, which allows me to insert a rod and then saw it to the required length. Very handy for getting it just right. Once cut, I'll use a file just to make sure the ends are nice and smooth. Here are the two hemispheres, looking great, and this piece is the special locking ring, printed separately in transparent just to hide it as much as possible. After applying a small amount of glue, it can be carefully fit into the bottom piece, and there's a little dimple in there to make sure that when you glue this in, it's actually in the right place, so that when you twist the two hemispheres together, they align correctly. I've deliberately not glued any of the rods or anything in place. They should only grip by friction, so that if you hold it while it's switched on, it won't go crazy with the motor running. And speaking of the motor, it's not even wired up yet. Okay, so we've built the frame and now we need to make it work. Now, inside there's two things we're going to need to power. Some LEDs to light it up and the motor. Now we already know how to light it up because these kits come with something like this, which has a coil of wire connected to a ring of LEDs. The other half has another coil like this, which acts as a transmitter. Now for this project, I'm going to use a special version of this. This special version has a touch-sensitive pad to switch it on and off. The reason I've chosen this one is if we're going to power the motor, we don't want the ball to be trying to spin whilst we're trying to balance it on top of the magnets. Now, we have two choices. We can either try and power the motor and the LEDs off the same coil, or we could use two, one for the motor and one for the LEDs. We're going to need to desolder the LEDs anyway, as I need to arrange them around that centre pillar. But in order to do that, we're going to need to understand how they're currently wired. This is the LED and coil wired up to the PCB with the 4 LEDs and 2 capacitors. This board receives the power from the transmitter via a big coil of wire, kind of like how wireless mobile phone chargers work. And this seems to be operating at a frequency of 100 kHz. When reverse engineered, we end up with this. It's a little strange, it kind of looks a bit like a
full bridge rectifier,
which kind of makes sense. Now, I have 3 different motors and I'm not quite sure which one's going to be the best one. They're currently running at 3 volts, but their specifications are: the top one at 6 volts should spin at 10 RPM, the middle one at 30 RPM, although it does say at 3 volts, and the bottom one at 300 RPM at 6 volts. The different speeds are mostly down to the gears at the end, and I'm wondering if the middle one is actually a 60 RPM at 6 volts. I'm going to start with some experiments. Firstly, to try and power the motor from the coil, and then secondly to see if I can get the LEDs lit at the same time. And there's 2 factors that affect how much power we can draw from this coil of wire. First is the distance from the transmitter, and as you can see here, the further away you get, the dimmer they become. The other is how far away the coil is from the magnet that's used to float it. The further away, the brighter it gets, but also the lower the ball will float. I've tested different magnet spacers starting at 2mm going all the way up to 5mm, and I've found that 5 gave the brightest light. After that it didn't really make that much difference, so on to the experiments. First, I disconnected the coil from the LED PCB and just hooked it up to the oscilloscope. The coil is about the right distance away from the transmitter, and we can see it's receiving at a frequency of 103 kHz and at 10.12 volts peak to peak. Now, adding the magnet back on top and you can see the voltage has dropped to around 6.2 volts peak to peak. This realistically is the most separation we can really tolerate anyway without losing too much power or just having a far too big spacer. Now, I'm going to connect this up to one side of a
full bridge rectifier
chip. I could have used discrete diodes, but this makes for a much more compact package. Let's just get those probe wires the right way around, and if I reconfigure the scope, you get a better idea of the DC voltage side of the circuit. The little marker here shows where 0 volts is, but we'll need to smooth that out before we can use it. Ignoring that for a minute, let's just connect up the 300 RPM motor and see if it spins. The problem we have here is the motor just can't handle that kind of waveform, so we're going to add a tiny little capacitor to filter it a little. This is 100 nanofarads, and as you can see, it's smoothed the waveform but the motor still doesn't spin. So I'm going to swap it out, and I've reconfigured the display to make it a little easier to see what's going on. When I disconnect the motor, you'll see the voltage shoots up to 2.9 volts and the line looks very steady. That is until I remove the tiny 100 nanofarad capacitor. I'm now inserting a 10 microfarad capacitor, and once again we get a nice flat line, but the motor still won't turn. The voltage is just still too low, but if we give the motor a little nudge, it does start to move, so that's progress. To test further, I've swapped in a 220 microfarad capacitor, and as you can see the ripple along the line is getting a lot smoother now, but we do need the motor to self-start. The problem is, whilst the voltage is fairly stable, it's just not enough to get the motor started. Once it's moving, it's fine. I also discovered that if I let the capacitor charge up to a peak of around 2.8 volts and then connect the motor, it also starts straight away too. So we need to find a way to raise that voltage just a little.
Full bridge rectifier!
Ah, cool. Converting an AC signal into a DC signal. But in this basic form they do have a limitation. Each one of these diodes will drop around 0.7 volts when it's in use. And because the signal actually travels through 2 diodes, we end up losing around 1.4 volts. So instead, I'm going to switch to using a single diode, which gives us a half-wave rectifier. We've lost half of the power, but it should increase the voltage by 0.7 volts. And with that connected instead, and without the motor, you can see the voltage is now sitting at 4 volts, which is much better. And with the motor connected, you can see it runs nicely and it's fairly stable, although I did find that sometimes the motor doesn't always start still. You might be wondering why it's 4 volts and not less. Well, I did cheat a little. The diode I used here is a 1N5817, which according to the datasheet is not a typical diode. This one has a forward voltage of 0.45 volts, a lot lower than your typical diode. Thinking about the motor stalling sometimes when powered up, for some reason gave me a thought. If you remember back to the LEDs and how they were wired, there were 2 capacitors directly across the coil, which I did think was a little strange at the time. Measuring them in circuit isn't always the best of plans. We get a value of around 48 nanofarads. So, just for fun, I decided to add the closest value I had, a 47 nanofarad capacitor, into the circuit, and look what happens. The motor just got way faster and the voltage for the motor has just jumped straight up. Now, my initial guess here is to say that the reason this happens is the capacitor forms an LC resonant circuit with the 47 nanofarad capacitor, tuning it to around 100 kHz, the same as the transmitter. So I decided to measure the inductance of the coil, and we can see that it comes in at 53.1 microhenries. And if I put that value into a resonant frequency calculator, along with the 47 nanofarad capacitor, we indeed get almost exactly 100 kHz. Anyway, the only other part now is adding the LEDs, and the first step is to remove them from the board. So now we need to wire them up and see if we can get the motor and the LEDs working at the same time. And I've had an idea about this. The motor is only using half of the AC signal, so what if I wire the LEDs such that they use the other half? Not sure it'll make much difference, but at least it'll be more balanced, plus this way I can smooth the LED signal, which might make them a little brighter. So I've wired that up to test it, and sure, the LEDs do light. Notice on the scope, one half of the waveform is perfect and the other is a little distorted. Well, watch what happens when I reverse the polarity to the LED portion of the circuit. Now they're both squashed. This configuration now matches my circuit diagram, although it didn't affect the brightness or the motor speed. In the end though, I removed the diode altogether. It really didn't seem to be making any difference with it in or with it out, so let's have less components. Oh, and the motor I'm using here is the 10 RPM motor. So, that means we're ready to start assembling the ball, but there's a few technicalities we need to check first, and this is about tolerance and precision. In order for the ball to spin, the pieces of metal rod need to be cut to the right lengths, or when this is assembled, the magnet at the bottom will actually catch on the outer side of the ball. Now, there's two ways around that. You can either keep cutting and filing the rods down till you get them just right, or you can print a load of different middle pieces all with slightly different inside lengths, along with some shaft couplers again with different inside lengths. Hopefully with these I can find a match, and after playing with them for a few minutes, one seems to work better than all of the others. And with that done, let's get on with the build. This thing inside kinda looks like a Dalek. Anyway, as you saw in the introduction, I have two complete Boing balls, and although they're identical, they don't behave the same. One of them needed an additional 3 diodes in series with the motor, or it drew too much current and stopped the LEDs lighting. Anyway, moving on, and I haven't talked much about the base yet. Like the previous one, I've designed it to look a little bit like the Amiga's A590 external hard drive. It's a bit bigger than the previous one, and there's a few sneaky parts in the design as well. On the left we have the lid, and the right we have the base. The lid now fits entirely over the base, hiding any of the seams. If I spin this around, you'll see a small indent here. This is where I plan to put the touch sensor, because on the other side this is where the little Commodore sticker will go. I've also stopped using threaded inserts, and this time we're just going to use self-tapping screws because it's much quicker. So let's put it all together. Now, you might want to add some washers under the screws for the levitating thingy just to push it up as much as possible. It needs to be properly sandwiched in there, so when you screw it all together it's as close to the lid as possible. I ended up adding 2 washers just to make it do that. Now, the last part of this is the ball assembly itself. But before that, given how I didn't like the look of the opaque plastic quite so much, I've decided to try something different. So I decided to print 2 sets of balls. and inside of them I've lightly sprayed one in white. Not too much, just enough to give a little light covering, and it's instantly obvious which one it is. I honestly can't decide which one I prefer. Let me know what you think. Maybe I'll just make two. Anyway, let's get the ball fully assembled. And this is really easy. I had to cut the smaller rod down by another 5mm to make it fit, and I've updated the template. This is because the 10 RPM motor is a little bit longer than the other two. You simply insert the longer rod into the bottom part, slide the centre rotatey Dalek thing onto that, you add the coupler to the motor, and then you add the other rod onto the other side of that. Then carefully you align the two hemispheres together and push. Oh, and make sure that when they get twisted together the red and white patterns are actually offset. And twisted together like this, they hold together nicely. Useful in case you ever have to make a repair or replace the motor. And now for the final test, showing both the original and the new ones. The new ones are slightly more difficult to get floating, but after a few attempts it becomes easy. It's interesting how the slightest magnetic field generated by each of these affects the others, causing them to start moving in unexpected ways. They're all floating nicely there, the new ones perhaps slightly lower, but that's expected given what's going on. However, when powered up, they really do come to life. It's a shame that I can't actually stop them from rotating around the base, so that they stay permanently facing sideways towards you so you can see them rotating properly. I'm sure there'd be a way to tweak this, but for now, this is just the result I wanted. And I still can't choose between either of them. Let me know what you think in the comments. It's somewhat rather mesmerising. Maybe it's because it seems impossible how this works, and you know what they say? Only the Amiga makes it possible. A nice little tribute to the 40 years of Amiga. Turned out pretty well, didn't it? It's not that hard to build, it's certainly easier than the original, although this does require a printer capable of printing multiple colours at once. However, you could always print it in white and paint the segments red afterwards to get the same effect. As with most of my projects, if you want to build this yourself, all the links to everything required are in the video description, and I hope you have fun building this. Anyway, I hope you found this interesting. Be sure to like and subscribe the video. Thanks for watching, and I'll see you in the next one.